Okay, everyone. So welcome to this afternoon session on graphics and geometric computing. So our first talk, so we are very happy to invite Professor Yang Kim from UR Women's University. And the topic is artistic robotic drawing on large non-planar canvas. Okay, so without further ado, let's welcome Dr. Kim.
Okay. So, thank you for the introduction, and also thanks for inviting me to this nice conference and nice place at BIMSA. So, just to get things started, how many of you here is working on computer graphics? Okay, two. How many of you are working on robotics? One. Good. You are very qualified working on both graphics and robotics. So this talk is basically robotics problems, but in the context of computer graphics. So if you are not really into computer graphics or robotics, I don't know how much you can follow me, but should be fun. Should be something interesting still to watch, even though you don't understand the underpinnings of whole things. So hope you enjoy it. Okay. So my talk, the artistic painting, artistic robotic drawing, was actually mostly from the PhD work of my recent PhD graduate, Down, and also my colleague, Professor Ivalo Ilkin at the Gettysburg College. So most of the contents taken out from her recent PhD dissertations. So you might have seen these kind of large wall drawings in different places in the world. So these are the examples in the wall paintings in Lyon, France. These wall paintings actually from my country in Busan and Korea. So you might have seen this kind of large wall drawings, of course drawn by humans. And the culmination of this whole large wall drawing is actually is this example, Gallery of Sistine Chapel in the Vatican City. I don't know if you visit here, but you know, this is really complicated drawing on large ceiling and wall on the Sistine Chapel created by Michelangelo in the early 16th centuries. But imagine somebody is asking you to draw this complicated drawing on the wall. It will be really hard, really time consuming. It will take a long time. Even for experts like Michelangelo, it took almost 4 years to complete this. So very complicated tasks for humans to create this kind of art form in the physical world. Of course, there has been some previous work on created robot-based art. One good example is this E. David, done by Oliver Doysen, very famous work, robotic painting. The other example is Paul. Some of paintings, robotic drawing is actually using watery medium or the oily medium, but some of paintings done using the pen art. Some of these are our work. But even though there are existing these kind of robotic drawing systems in the literature, it will be really hard to replicate large world drawing in a real world settings. So our research goal here, that the main focus that I'm talking about today, is how we can create a robotic system that is capable of drawing a pen art on general non-flat canvas surface in the world using existing high degree of freedom robotic manipulators. Some manipulators are equipped with dual arms. Some manipulator has a mobile platform attached at the base, so they can freely move around to cover a really large space. So that's a problem that we want to tackle these features. And that's something that I wanted to discuss. So here is a kind of short preview of the or summary of the talk that I'm going to show or talk about today. So let's watch just for a couple of minutes. There is some sound, but it's not really important. You cannot hear it, but yeah. Okay, so now that's kind of a quick preview of we have done for this artistic robotic drawing project. Now, to create this kind of system, we have to address typical challenges encountered in the robotics problem, which include sensing, planning, and control. These are very typical problems that are dealt with in the robotics area. So in our case, for the sensing problem, of course, we have to somehow reconstruct the target physical canvas so that we can draw something on that target surface. That is sensing problem. We have to reconstruct the canvas geometry. Once you figure out the geometry of the target surface, now then you have to generate or obtain a drawing path. This path could be provided by artist or can be even created by AI or whatever. So you have to generate the path or the pose sequences for robot to actually draw on the physical surface. That is like a planning problem. And another planning problem that we have to address is that if you want to cover really a large canvas, robot cannot be just fixed at one place. It has to move around. Then you have to find out where you have to put the mobile platform of your robot at some position so that it can cover a certain portion and then move to the next location. So it's more like a coverage planning problem for robot. So you have to find the robot configuration to cover the target canvas. And then finally, this control problem is that no matter how good you are in the sensing or reconstruction, there will be always some errors involved in the reconstruction, right? It depends on sensors or your algorithm. So you have to somehow cope with those uncertainties from this sensing. In our case, we use robotic control to compensate for those uncertainties that may exist in the sensing or even the robotic motions. So you have to answer all these questions to successfully create such a system. Now, this is like kind of overview of our robotic drawing system. So as input, we typically take rest images. So consider two steps. One is creating a drawing path and actually executing on the physical canvas. Creation and drawing. And as a typical input, we take the rest images as an input to our robotic drawing system. So these input images can be drawn by artists or can be generated by AI or generative AI. But these typical rest images is not a good form for robot to actually execute drawing because these are pixels, a bunch of pixels. So you have to convert these rest images to kind of in a vector form or a trajectory which robot can execute to actually create draw, right? So that's the role of the path planner. And then, of course, you have to figure out the canvas geometry, right? That is canvas estimations. And in our case, this estimate canvas will be stored in the quad tree type data structures. Then this path planner can execute actually on that canvas estimation. But now you have path and you have 3D geometry, and you have somehow mapped this 2D drawing onto 3D. This problem in computer graphics, I know there are only 2 people in this room working graphics. This problem is known as texture mapping in computer graphics. So we have to figure out this texture mapping or drawing surface mapping problem going from 2D to 3D. So surface mapping problem. Now that everything is mapped to 3D drawing, then now robot has to find out the robot configurations or joint motions to actually create this robot motion. That will follow for the rest of the pipeline. So that's the pipeline that we are following. And now I'm going to going over each of these steps a little bit into more detail. Okay. Now, first part is drawing path generations. So in our work, we consider 3 types of drawing path generations. This path, it will be, of course, 2D vector sequences of points, which define piecewise linear path. Okay. So the obvious choice for drawing path is something that it is generated by artist. That's the easy one. Another interesting aspect of our drawing path generation step is that given some rest image, we create so-called the TSP art, which is basically find one single continuous line of path that kind of approximate the given input image using different colors. That's what is known as TSP art. And the other one is, this is also very well known in computer graphics, which is called the stroke-based rendering. So here we need to find out a bunch of stroke sequences that approximate the given input images. That is stroke-based rendering. So we use all this method to create the 2D drawing path. Again, the very obvious choice for creating drawing path is done by the artist. So you can use existing vector drawing input, such as Adobe Illustrator, or in our case, we have our in-house vector graphics engines. Or if you're into computer graphics research, there has been very nice work about converting rest images to vector images in the literature. So you can even use that to create 2D vector form of images. That's obvious choice. And another choice is, again, this is our choice, of course, is so-called TSP art. And again, what is TSP art? TSP art is given some original images. We want to find a single long continuous line without crossings, which approximate the original inputs. That's so-called TSP art. And typical in TSP art, the way people try to attack this problem is, first of all, we somehow estimate the original image, the tonality of the original images using a point distribution. And so kind of approximate the original input with this so-called stippling points. Once you generate these stippling points, you can use these points as input of a site input to the TSP and then use a fast TSP solver to visit each of these points, then you can generate TSP solutions. So that's kind of typical steps to create this TSP art from the original input images. So we follow basically this approach as well. And this is some existing TSP art done by somebody else. There are people of artists who works on this kind of problem. So TSP art. But in our case, we are a little bit different because we want to create TSP art in colors, not a single or grayscale or black and white lines. So then we need a different color space. So in our case, basically follow the same approach, but given this color images, we find kind of because you have to use a robot to replicate these original images. You cannot ask a robot to choose some arbitrarily many colors. In other words, the color space for robot drawing is limited, so you have to somehow choose the limited color channels to approximate the original color space using different color channels. And for each color channels, we follow the same step, following the approximating stippling points and generate the TSP lines for each color channels. And then we add up, we accumulate them, then we have the final one. So this is how we do it. So the first thing that we have to do is that since the typically robotic art form, we have only limited the color brushes or pens. So you have to find good candidates of color channels to approximate the input images. In our case, we use two different approaches. One is CMYK, which you might be familiar if you are using a color printer. They are using a CMYK. So regardless of the color spaces used by the original input, we can just choose a CMYK, and we use the CMYK color space to approximate the original color space. That's one way. And the other way around is that we kind of use color clustering to optimally find the representative colors to the input original images. That might be another way based on color clustering. We use both. And then point generations. Since we have very limited attendees who are doing computer graphics, probably it's not a good idea to get into too much into computer graphics. But once you find the color channels, now we have to solve this point stippling problem. So here, basically, what we do here is that these points should represent, the point density should properly represent the brightness level of the input image. So if the certain area is too dark, you may need more points. Certain area is not that dark, you just need a few points, right? So based on that heuristics, we can create these points to approximate original inputs. But more technically, we use a weighted Voronoi diagram. So certain Voronoi diagram, you need to subdivide recursively, subdivide more. In other region, you don't. So that way, for each color channels, you create this points or point stipplings. And then for each stippled points, we independently solve the TSP. And in this case, we are using the existing best TSP solver, like Concord solver, which is basically formulated as linear programming. So we use TSP solver to find the TSP solution for each channel, and then we combine. Now, compared to the original image, the final result obviously not exactly the same, not identical. Kind of rough, but you may think of this as some kind of art form or maybe just rough approximations. Now, that's the typical output of TSP art, but in our case, this is not sufficient for robotic execution, because if you use the steps that I just described to provide it to the robot, this path may have quite jagged edges with sharp corners. This is not a good situation for robot to execute the path, because you have to, the robot and the effector has to quickly switch the motions, which means that you need a really high accelerations to follow it, which is not good. So we need some kind of path smoothing or path optimization, which basically cuts an area where you have high curvature. So we use a simple decimation algorithm to cut those high curvature area to have more smoothed sequence of vectors. Also, we're using Bayesian patches to have more curvy curves. So that's the TSP art. And then the last one, the final kind of last way to generate, the final way of generating this drawing sequence, drawing path is so-called stroke-based rendering idea. So stroke-based rendering is a very well-known non-photorealistic rendering idea in computer graphics, so which basically solve this problem. So given this input image, find the sequence of strokes, usually typically fixed number of strokes to approximate original images. That is so-called stroke-based rendering idea, basically. Of course, this has been studied for a long time, like even like 98, quite old or very well-known technique. But in our case, the main departure from this stroke-based rendering idea is that we want to mimic the way humans actually draw strokes in the painting. So if you keep that in mind, human never draws strokes randomly here and there or there. People never do that. People have some tendency or they'll have their own rules to draw, right? So we take this stroke-based rendering, but we are more interesting to generate the proper ordering of sequences, strokes, not just random sequences. So that's something we have to solve in this case. So again, stroke-based, what is stroke-based rendering? Stroke-based rendering is, input image, find a certain number of strokes to approximate the original image. But in our case, we consider the drawing sequence, not just finding strokes. Now, if you think of this problem, since I presume there are many AI folks here, including Professor Yu. So, well, maybe you can use AI or machine learning techniques to mimic the way people draw something, right? But then here, the main problem was we don't have such database on hand, especially for high quality drawings. I mean, there are databases like quick draw dataset, kind of sketch type simple drawing. There are such database which contains drawing sequences. So you may use a simple database to do something to solve this kind of problem, but that would not really work for artistic drawing or this complicated drawing. So in our case, instead of relying on the kind of data-driven approach machine learning approach, we are relying on a kind of rule-based approach. So we have our own rules for drawing or create these drawing sequences. So here is our pipeline. So given this input, we find salient objects based on image segmentations, more specifically panoptic segmentations to figure out which objects is more important than others. And then we also, for each segmented object, and we find so-called superpixels, which are kind of a grouping of pixels which are perceptually similar. And then at the same time, we also estimate the depth of the input image. And then we combine these two to create a drawing sequences. So this is kind of our own rule to create these drawing sequences or stroke-based rendering. So more specifically in panoptic segmentation, if you're familiar with this, if you use existing panoptic segmentation, you can label each pixel with so-called things and the stuff. And things are more like objects that you can count the number. So like shapes or humans. Or other, like stuffs are more like something that you cannot count or kind of abstract, which has similar texture or material. So you use a panoptic segmentation to first of all label each pixels. And then we have some kind of ordering. So things that you can actually count, like human and dogs, we sort these objects in terms of the pixel area times segmentation confidence. We have sorting for these things. And we also have a sorting for this stuff based on the semantic ordering. And things has higher precedence over stuff, higher priority. So we will draw things first, and then stuff. And then for each segmented object, again, we group the perceptually similar regions we call superpixels, and that will be kind of starting point for each superpixels. That will be starting point of strokes. At the same time, we have you use a depth map, which can be used from like a back to front drawings. So based on depth, we will draw something farther and then closer and closer, closer. So if you combine both, you will have something like this. So things first, but back to front, and then stuff. Well, so depending on who you ask, this may not be the way people draw. It depends, but I think we are okay. So that's the kind of third type of input generations. And then next one is once you have this input of a 2D sequence of path, now we have to, so we have this 2D drawing, now we have to map it to 3D, which corresponds to the real physical canvas. But then, of course, you need this physical canvas first. You need the data, or you need a model of 3D physical canvas first, right? So that you can map it. In our case, we consider two different approaches. One is so-called the sensing by context. Since the main aim of this idea is use the robot to draw, why not you use a robot to figure out the canvas geometry by touching, okay? Because these days, a lot of these manipulators are equipped with a torque sensor or force sensors at each joint, so it can sense whenever it touches target surface. So by touching it, you can kind of measure the height from the ground plane, so which is known as height field in computer graphics. So we touch a bunch of places, kind of context sampling of the target geometry. And then we store at some kind of proximity data structures, like in our case, quad tree or KD tree, so that some random points which were not sampled can be approximate using typical bilinear interpolations. So some point can be interpolate with these neighboring sample points, so that you have a rough geometry of your target canvas. So that's so-called sensing by contact. So this is actually the execution. So whenever the robot touches, when it feels some opposing forces, it stops. So that way, you can sample the target geometry. And then another choice of reconstructing target canvas geometry is sensors like RGBD camera. So this is obvious. Using RGBD camera, you can maybe reconstruct the target geometry, right? That's easy, obvious one. So in our case, we use both. So then you have some idea of the target canvas geometry, and you have 2D path. Then you have to map it to 3D. Now this is a texture mapping problem. But you know, in computer graphics, it is well known that to diminish the mapping artifact, you have to use some kind of conformal mapping type stuff to reduce the angular distortion. So in our case, we also use the conformal mapping to reduce the mapping discrepancies. Conformal mapping was used. More specifically, we use the least square conformal mapping to go from the 2D and 3D. Now, this is the result of mapping. So this is input 2D drawing sequence. In this case, it's some pattern. And this is actually the drawing result on some circular walls. And if you do not use proper mapping technique like conformal mapping, you might end up with this orange line, which is just slightly off from these black lines, which preserve the better shape for the original inputs. So there is difference whether we're using conformal mapping or not. So that's the second step. So now, so far, we create 2D drawing, map it to 3D. Now the next step is you have to use a robot to actually realize the drawing. That's robotic curve rendering. Now, to tackle this problem, this is actually a trajectory plane for robotic, in this case, robotic plane. So we have 3D path on the target geometry. Now, according to our study, it is best to, for the end effector of a robot, to approach to the perpendicular to the target geometry. That's the best way to actually draw it. So, which means that the configuration of end effector is actually can be easily determined from the path. Right? So we know where end effector should be located. But you still have to figure out the rest of joint angles of the manipulator. So this is a so-called IK problem, as you may know. But the difference here, or the main issue is that this IK solution should be continuous in configuration space. You have in the continuous motions. So this so-called pathwise IK problem. So we need to solve this pathwise IK problem in configuration space, basically by minimizing the configuration distance in the configuration space, so that we have smooth motions for all the joints. So if you do this, now you're almost ready to draw something on the physical surface. But unfortunately, this is not sufficient depending on how accurate your sensing is. If your sensing or reconstruction is very accurate and very precise, if you follow these motions, you can create it. But if your target geometry, the physical geometry is not really as precise as what you hope for, if there is some discrepancies, the robot may not even touch on the target surface because the robot thinks that there is surface, but they may not be, right? Also, if you have really bumpy surfaces, it's really hard to follow on top of the surface, especially if you do not have really dense samples. So in our case, we solved this problem, this uncertainty problem using so-called impedance control. Okay. So impedance control, as far as I know, is not very well used in computer graphics, but robotics is very well known, especially for haptic rendering. So the impedance control is basically like a virtual spring. The robot arm acts like a virtual spring. Right? The robot arm is like acting like a virtual spring. In other words, you can control the stiffness of spring depending on how you want. So in our case, we allow high compliance spring motion on the approaching directions, but we impose really high stiffness on the tangential direction, which means that the robot, or in this case, pen tip, can move really freely along these perpendicular directions, but not tangential directions. We have this mechanism. And then when you estimate the geometry, you kind of intentionally underestimate the target geometry so that your estimation is a little bit under than the actual geometry by offsetting. So that robot then will try to reach this underestimated geometry. But since this robot has compliance in the perpendicular directions, whenever it touches on the surface, it will stop. But on the tangential direction, it has high stiffness so that it can still follow the curvy motions. So this way, we can compensate a little bit loose geometry reconstructions on the surface. Okay. And then the next topic that I want to discuss is now, this is also, the earlier one is control problem. This is planning problem, which is that, the main target of our problem is we want to draw something on really large canvas. To cover this large canvas, we need some kind of mobile platform attached to the base of robot so that robot can move freely. So it can cover a really large space. Right? That's obvious. Then, for robot, even for mobile platform, for at a fixed position, what the robot can draw is limited, right? So this is what it calls coverage. So when a robot is positioned at a certain position, the robot can reach is limited. It's a so-called coverage. Now, then let's say this is our target surface that the robot want to draw, right? But when the robot is fixed at some pose, this coverage will correspond to, for example, these portions. But here, since the robot needs to draw all these spaces in the canvas, we need to find out the pose for the mobile base, right? So that robot can draw here, or here, 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 there. The robot should move at some positions. Now, this problem can be reformulated set cover problem. Because imagine this is the entire set. You have a limited coverage. We want to find the entire set using a certain number of elements. So this is set cover problem. And I mean, this is a hard problem to be optimally solved, but we don't really need the exact solution. So we need to rely on a much simpler solution, which is greedy type work. So main idea is that instead of trying to solve this whole problem in 3D, you want to reduce to a 2D problem, like basically reduce the dimension 3D to 2D. So we, for the coverage of this manipulator, upper manipulator, we approximate that coverage using a simple circle. And also for the robot base, we have also simple circle approximations. And also for target surface, we also reduce this dimension to a 2D by projecting onto the ground plane. And then the question is that, can we find a set of circles or the coverage circles to cover the entire camber geometry? And in our case, we use a simple gradient algorithm so that here, the simple solution is that we just randomly sample these circles of coverage such that they cover the entire target surface. And then we greedily select these circles one by one, which can maximize the coverage of the uncovered area so far. So this circle covers this portion. And the next one will cover here, and the next circle will cover here. So kind of in a greedy fashion, you can find this set of circles or coverage. So from this coverage circles, we then find the robot base, kind of using, again, similar to inverse kinematics. So this is where the robot base will be located. So on. And now this is illustrations. So here you have this target geometry, and this is robot coverage, and this is base, and some other canvas geometry. And this is actual execution of robot on the simulations. So robot, we need to find this pose for the mobile base, so that when the base is stationed here, it will draw a certain part and then move to the next pose to draw the next part and so on. So they can draw the entire area. Okay. Now, I think I covered most of the technical aspect, and I'm going to show you some results. So here is a robotic setup that we're using in our labs. So one is, again, the kind of mobile manipulate type. So manipulator attached to a mobile platform so they can freely move. And the other one is dual robot arms with the pen switching mechanism. And with the typical software setups. And this is some demonstration of working of dual arms with drawing tool changes. So that depending on the color, you will switch to different pen colors. And now this tool holding or pen holding mechanism is actually 3D printed. And one issue we had to deal with is that since we want to replicate the drawing, so the pen should be held very firmly. If you move slightly loosely, the drawing will be whole messed up. So we find out some mechanism. We figure out some mechanism to quite firmly hold the robot or drawing pen, also change more easily. And this is some results of drawing on some arbitrary surfaces in water tank or half sphere, a water bucket, or a parking cone, things like that. And this is the execution of those results. Another drawing results on the circular column with a lot of bumps on the surface. And some data statistics. And this is sequence. Okay, now this is results for TSP-pen that I described earlier. And this is input, original image, and the robotic realization of TSP-pen on paper. And another result. The left is input, original, the right is TSP result. And some statistics. You know, if you see these data statistics, this computation of finding the stippling points or solving TSP is quite short compared to actual drawing. Drawing will take most of time. So this is TSP drawing on a mobile platform. And now this is the result of stroke-based rendering. So here, what you need to see is that we want to emphasize that not only the drawing result, hopefully it would be similar to the input, but the way the robot drawing or the sequence that the robot follows to draw we claim that is similar to what human draws. Okay, this is on statistics. And then the last one, I think, is the larger scale drawing. So, yeah. So again, the robot is shifted from one pose to another pose to draw on this curvy wall. Okay, this is something that you have seen earlier. Okay, so I think I'm almost done. So I basically talked about our robotic pen art drawing projects that generate artistic pen drawing on non-planar large surfaces using different input data types without minimal distortion from this drawing to 3D. We were able to achieve artistic drawing even with uncertainties in the sensing or in the contact geometry using the impedance control. Now, finally, I want to say something about our work that is, even though the main focus is on the artistic robotic application, but this type of work is not only limited to the artistic robotic application. Whenever you need continuous contact between the end effector of robot and some target surface, which requires a long sequence of path, you can use this technique. Good example is robot milling. You want to smooth out the robotic surface by continuously moving the end effector of the surface or sanding. That can be applicable, which is also a very good application. So that's the end. And I want to thank my students and collaborators and funding agencies. Thank you. And now I'm going to leave kind of art exhibitions that we did last year using all those systems that we developed in this project. And we rented this nice art studio in our campus and invite people to see the actual actions to better appreciate what we did. So thank you.
Thank you, Professor King. And so now it's the Q&A session. So any questions?
Okay, thank you. So when you are doing the stapling, how can you control the number of the points you generated?
Well, in our case, it's just easy. Just enter the number of points that you want.
Oh.
Yeah. So whenever you reach the number of threshold, we just stop. Or you can even provide the accuracy or error limit that you want to kind of endure. Then you can just stop it. It does depend on, this algorithm is based on the Voronoi diagram, right? So depending on the
more points, can your TSP-art be better?
in the extreme, each point will be exact same as the input. So right. So if you have an unlimited number of points, the input will be same as stapling. So, yeah.
A very simple problem. So I noticed that you will spend a very long time drawing a not so big picture. Is it because your number of strokes is actually like much more than a real artist drawing, or is it the robot moving too slowly?
The simple answer is the robot is moving too slowly. Because, the robot here, you see that robot is drawing on the paper. So if the robot is, yeah, real speed, yeah. If a robot is moving too fast, the pen will be torn apart. So, yeah. So you cannot just, also you cannot push too hard. It will be torn apart. So robot has to be careful. So otherwise, yeah.
More questions? Okay, so during the drawing, if like because of some accident, like the canvas moved a little bit.
Yeah.
So is there a way to continue drawing by some perception methods?
In our current setup, we don't have any sensor feedback installed. So if you have some kind of sensor feedback to check whether the target has slightly moved or there's kind of some intervention from human, maybe you can use that information to compensate for the change. But
so
currently,
is it possible to draw like based on something already on the canvas?
You mean kind of interplay?
So maybe the canvas, so there is already some drawing on the canvas.
Okay. I mean, if that is relevant to what we are trying to draw, we may take that information to refine the next drawing. But it's totally irrelevant. I guess there is more like an AI problem how to mix two drawings to make sense out of it. Yeah, that's actually something that we are working on, like collaboration between human and robot.
Yes.
So human is drawing first a little bit, and then later robot participate to complete the rest of it.
Yes.
That's actually a good direction. And now actually some people are working on that problem these days.
I have a question. And for the TSP drawings, and we separate the picture into 4 colors, right? For example, if the yellow part it has many components, how do we handle this? Yeah, it's just like there is a yellow part and here, and the TSP problem.
Yeah. In that case, you have a little bit weird artifact from here. I mean, you think that this yellow region is quite separate from another region, right?
Then
So you have a little bit weird, the straight line.
How can we handle this problem?
I mean, we cannot handle it. Just if this weird line will be drawn, but if that occasion does not happen often, since you have overlays of different color channels, it will be kind of unnoticeable because we have many color channels on top of it. So if you're just single straight long line, it may not be very visible.
Thanks, Professor. So my question is, the process we have seen is, for me, it's more like printing. We already have the picture or the paintings, and we calculate the sequence or the strokes. So I think maybe it's possible to, for example, have some cameras and how human artists will draw a picture, they will refine or adjust the painting while they are drawing, by seeing what they have done. So I think maybe that's a way to make the robot really drawing something.
Yeah, you mean the robot is responsive to the human input. Yeah. That's something I said earlier. So participation of a human interplayed with the robot drawing. Yeah. That's actually a pretty good direction. Actually, that's something that we are pursuing now.
Thanks.
More questions?
Yeah, thanks for the great talk. I also have a question about future direction. So I was wondering if you have considered to extend drawing a 2D art form to the like a 3D sculpture, like 3D printing as well on the arbitrary planners or some lamp or somewhere else as well.
Yeah, I think it's possible. This is, again, I said a little bit about the milling at the end of my slide. So now we have a pen attached to the end effector. So if you replace the pen with drilling or some removal type devices, you can extract some unnecessary part, and eventually we'll have some kind of 3D sculpture.
Thanks, Professor. And I have a question that in the TCA arts, I was wondering that if we can change the thickness of the pen, maybe if the line is thicker and can be better at simulating.
Yeah. So that is something that we also thought a lot about it. So can we change the thickness of pen such that we can reduce the number of strokes, for example, or reduce even the number of the vector sequences? But again, that's also depends on the physical medium that we want to draw. So if the pen is too thin or too thick, you cannot hardly see the final result. Or if the pen is too thick, you can easily tear apart the paper. So somehow, empirically, you find out best thickness of the pen, which does not destroy the paper. And another thing is that if you have to change the pen thickness, you saw the pen changing mechanism, right? So you have to change from one thickness to another thickness. So it will also cost you another time to switch from a pen another time. So you may reduce the number of the sequences, but you have to change the pen. So eventually it takes more time. So kind of trade-off. So we end up with the constant thickness in our systems.
Okay. So,
Professor Kim, that's fantastic talk. I have a rather general question. So your robots, are they, which stage you would expect to produce value for the current artistic market? I mean, the ideation part, the reproduction part, or I mean,
Yeah.
it looks to me more like industrialized art
Yes.
production.
That's actually a hard question. You know, artists are generally poor, so we cannot really talk about money here. So that's why I brought up this thing. This is a purely industrial application, like milling or sanding, which has really has a lot of big industry, right? The milling is a very important area, like manufacturing and all those areas. So if you need a very precise milling, which have a long sequence of milling operations, this would help. And yeah, that's something that I can tell you about. Yeah. Even though it's based on the artistic motivation, there are some industrial applications which we did not pursue by ourselves. Yeah.
Thank you. Anyways, thank you.
okay, I guess because of the time constraints, let's just end here. And if you have more questions, you can talk to Professor Kim like after the talk. And let's again thank Professor Kim for the wonderful talk.